Hello there. Today we're looking at Language Models Are Few-Shot Learners by Tom B. Brown, Benjamin Mann, Nick Ryder, and Melanie Sabaya, and a whole slew of authors from OpenAI. This paper, also called GPT-3, just came out recently. So GPT-3 is a model that is a language model, and it comes out of a succession of language models of OpenAI. And this paper is basically an investigation into what you can do with giant language models. Now, this language model is an order of magnitude larger than anyone has ever built a language model, and it can do some absolutely crazy things. So we'll basically go over the architecture, over what the model does, and over the experimental results. It turns out that if you train a language model on enough data, it is able to solve NLP tasks that it has never seen just out of the box. And we're going to look into this very cool kind of formulation of the problem. As you can see here, the paper is 40 pages long without the appendix. It needs its own table of contents, which is crazy. So we're going to skip a fair bit of things. So first of all, what is a language model? For those of you who don't know, I've done a bunch of videos, and you can see those in my natural language processing playlist about language models, and specifically about transformer language models. So a language model, let's just take an example, this sentence right here. Just the sentence as such, like, third, humans do not require large supervised data sets to learn most language tasks. Right? This is an English sentence, and a language model would be a model that if you cross out a portion from the end here, like this right here, it would be able to tell you what comes next. So in a language model, you would input this part right here, and it will tell you the next word is data sets. So that's basically all a language model does. And once you've trained one, you can basically generate word after word after word from it. Or you can ask it a question like, which word is most likely to come next, or more likely? So a language model is nothing but a model that can kind of generate language in a probabilistic way. And the cool thing about language models is that you can train it on any sort of text data. And that's what they do here. So they train a language model on giant amounts of data. Specifically, right here, they go into the data sets they use. They use this, let's skip down. They use this common crawl data set, which they filter down for quality. And this is basically a crawl of the entire internet, if you will, together with these books data sets and the web text data set and the Wikipedia data set. So they throw all of this text that they scrape from the internet together and then train a language model on that. Now, the language model right here is called GPT-3, and they train various sizes of it, and we'll get into how it's built in a second, but just compare this to a language model like BERT. BERT required this much flops to train, and this is a log scale. So this is right here, this is several orders of magnitude larger and bigger model, and is trained for way longer on this text. So naturally, it is going to be a lot better at language modeling. You can see right here the size of these models that they trained on. Remember, the previous largest language model, the Turing NLG of Microsoft, had something like 17 billion parameters, so it would be comparable to this right here. Whereas GPT-3 has 175 billion parameters, which this is absolutely crazy. This is an order of magnitude higher than anything that's ever existed. And if you look at the last GPT, the GPT-2 model, that, if you remember, I've made a video about it, is too dangerous to be released. Well, now it has been released, but was too dangerous to be released. It clocked in at about 1.5 billion parameters. So compared to this GPT-3 XL model right here. They train these multiple models to basically estimate the effect of the model size. And you can see here the largest model has 96 attention layers. Each layer has 96 attention heads, and each head is 128 dimensional. And it trains on batches of size 3.2 million. This is the batch size. Absolutely crazy. So they train this on a giant distributed cluster that apparently is provided by Microsoft. And yes, crazy things. So how does this model look? This model is a transformer model. And right here, we don't even have like a description of a transformer model. It's just assumed you know what that is. I have made several videos on transformer models, and especially things like attention is all you need or BERT or something like this. But for those who don't know, if I have a transformer model and I want to build a language model from it, and let's take this sentence right here, I would input what's called a context, which is the thing I already have, right? I would input that into a transformer model, and a transformer model is just several layers of attention mechanism. Now, an attention mechanism is basically a way where information is routed in between the different tokens right here, and as it goes up the layer, basically the information is routed around and the model can make various inferences. And at the end, the model is supposed to come up with the next word that you're going to put here. Specifically in this paper, they use subwords like word piece tokens, like it is common in NLP right now. But essentially, this is an autoregressive language model. So it's not like BERT, it's not bidirectional. It is autoregressive. It goes from left to right. It always produces the next word. It is like GPT-2. They even say this. They say, we use the same model and architecture as GPT-2. They just have more layers and wider layers and more data to train it on. So, how do they train it? Okay, we already said they train it in simply a language modeling way. Just next word prediction. That's it. Okay. So it's not even something fancy like BERT. The interesting part is when you do the single tasks. So what you usually did with something like BERT, you would do first pre-train. So there this is the language modeling right here, this pre-training phase, where you teach BERT about the English language by just feeding it a lot of data. And then second, you had a step called fine-tuning. I can't even write tuning. So on the second one, you'd have something like the task you're actually interested in. And let's say the task you're actually interested in is sentiment classification. So in sentiment classification, you have like a sentence like blah, blah, blah. And you want to know, is that a positive sentiment, like is it a happy sentence, or is it a sad sentence? And you would have a database of labeled instances of that. So in this database, you'd have a bunch of sentences, and for each one, you would know, is it good, is it positive, or is it negative? And then you'd have like a smaller test set right here, and you would basically take this pre-trained model, train it on this data set in a supervised machine learning way, and then test it on this test set right here. This is called fine-tuning. That's what they display here. So in fine-tuning, the model is trained via repeated gradient updates using a large corpus of example tasks. All right? So the example task right here could be translating to French. So in your training database of the translation task would be sea otter is called loutre de mer. And then you'd actually change your model. You do a gradient update. I mean, if you're in the NLP world, this seems very natural, but they are going to argue in a second that this isn't the only way that you can teach a model a task, right? So this seems very natural, right? You're going to change your model. You take your pre-trained model and you're going to fine-tune it on this task. And if you have a different task, right? If you have now question answering task, you're going to have a different data set right here with a train and test data set. And you're going to take the pre-trained model and then fine-tune it on that data set and evaluate it on that test set. So this gives you basically with as many models as you have tasks, and for each one you need a big training data set in order to perform well. Sometimes we have this, sometimes we don't. What they are interested in is basically to take the pre-trained model and directly go and evaluate it on the test data set in a sort of a zero-shot fashion. Now, it is not zero-shot, as they will argue. So what are they doing? In a true zero-shot fashion, you would just take your language model that you pre-trained and you just input the following text. You input what they call a task description and a prompt. So this is the input, and you simply ask the model as a language model to predict the next word. It's just what comes here. Now, what you're counting on is basically that in the training data, the model has seen a structure like this enough to understand what's going on. So that in the training data, somewhere in the internet, there was the structure of translate something to something, and then there would be a word here of something, and it kind of has to realize that this goes here, like that the next word. So basically what you're asking it is, if you were to find this text on a website or on Wikipedia or in any of the books dataset, if you were to find this piece of text, what would be the next word in that piece of text? And you kind of hope that this is enough, if you've trained a good language model, that this is enough to actually produce the French translation here. Now, before I realize I've said the language modeling is to teach the model the English language. It's actually not true. In this Common Crawl corpus, you also have many foreign languages. So you basically teach it a general model of the internet. Now, they contrast this to what they call one-shot learning. So in one-shot learning, you not only do you have the task description right here, and this is a string, right? You don't specifically tell the model that this is now a translation task. You simply input this as a string. So not only do you have the task description and the prompt right here, but you also have one example. And the example, and this is where they bring in where they say it's not exactly zero shot. Where's my little drawing here? So the example is going to come from the training data set of the task that you're interested in. But the important part is you never train on it. You never explicitly train on that example. You simply put it in the context. So you simply put this string. So translate English to French, new line. Sea otter is l'outre de mer, new line. Cheese is what? You simply input that string into the model as a language model, and you ask it, what's the next word right here? Okay, so I hope this is clear. This is what they call kind of one-shot generalization, and by one-shot, they basically mean you simply provide this thing in the context of the model as a language model. Now, the advantage here is immediately clear, that you only have to train one model, and then basically at inference time, you can just input the task description and the sort of training data for the task into its evaluation context and the task itself. And it will, if it really does what they claim it does, it would be able to sort of understand the prompt here, understand what it means to translate from English to French. It would look at this example and say, oh, that's what you want me to do, okay. And then it would be able to generalize to this input right here to say, okay, from the task description and the example, I get what you want me to do. The next word here is cheese. What's cheese in French? I don't remember. Fromage. Now, the way the language model is going to interpret that is slightly different. As we said before, the way the language model is going to interpret is, if you were to find the following text on a website somewhere, the text is called translate English to French, new line, sea otter goes to l'outre de mer, new line, cheese goes to. what would be the next word on that website. So that's what the model sees, right? You have to differentiate between what the human wants and what the model sees. The model is just a language model that is going to take the next, that is just going to determine, if I were to see this text somewhere, what will be the most likely next word. So you have to phrase your tasks in a way that makes sense in that thing. And they also have this few shot thing where you not only provide one context, but you provide a bunch of context to basically tell the model more of what it should do. Right? Now this doesn't only work in a free mode where you basically say, what's the next word here? What you can also do, if you have such a language model with the exact same model, you can give it basically a couple of possibilities. So you can give it you can say like it's either chat, or it's fromage, or it's hôtel. I think that has like this. So you can basically restrict it to only produce one of these three things. So in translation, this might not be, you know, the way to go, but if you have like yes, no answers, questions, you can restrict it to that. So in a lot of these NLP tasks, you have some options given for a given question, and you can also restrict it. So don't, you know, you always have to go with the task at hand. But this is in essence what the model does. And this is, I think, this is the new, well, not the new per se, but this is one of the core ideas of this paper, if you take anything from it. There's no new architecture right here. There's no new wisdom in training. They train in a standard way, in a standard language modeling fashion, a standard transformer architecture. This just happens to be ginormous, okay? This right here, this thing where they say most of these things would fine-tune and then basically end up with one model per task, and you need a big data set per task. But we simply can do this. Since we have such a large language model, it is basically already knows how to do these tasks. As long as we formulate them in a language model way, we can have the model perform these tasks. And they will show that this works surprisingly well throughout this paper. Now we get into the experimental results right here. And the experimental results, first of all, on language modeling, as you can see here, they basically say as you go up with the parameters, you see the more yellow ones are the parameters, you go into your validation loss goes down and down and down and down. And I believe this is sort of a log scale as well. So this is the log probability, so the perplexity, and that this basically follows a trend. Oh no, this is a log scale. This is a log scale. It follows a trend where as you scale up the model and as you scale up the compute that the model gets, and we know for these big language models, we basically know you have to scale up model size, compute time, and data set size in the same fashion for them to make these gains. But if you do that, it follows like a power law where as you scale up these things, the model basically gets better and better and better. And the question, of course, is, you know, how far can we go with this? But for now, it seems to hold quite well that you can just make improvements by scaling up your model on language modeling, at least. So, where do we basically go from here? So before we dive into the actual results of the individual tasks, so now they're going to formulate these individual tasks. So they have like pure language modeling tasks right here. Like Alice was friends with Bob. Alice went to visit her friend, and then it's like, what's the next word? Okay, is Bob. And George bought some baseball equipment, a ball, a glove, and a. What's the next word? And I guess this should be bat right here. But we're going to go into the tasks, and one of them is, for example, question answering. So in question answering, you simply get either you get just a pure question or a context and a question. And they do the facts, they test where a situation where you just get the question. So you just get, I don't know, who is the Queen of England or something like this. And the model is simply to produce either the result direct or to choose from a bunch of answers which one is the most likely as a language model. And as you can see, as you scale up the language model, the zero shot, one shot, and few shot predictions. So in few shot, you give 64 different examples from the training set in the context. So you always have, so your context is going to look something like this. And they have examples at the bottom. I haven't looked at the QA task, but the example is going to be something like this. You have a task description like answer the following questions. Answer the question. And then you have your example. So in zero shot, that's 0. In one shot, it's 1. That's what I like. And then you say, how tall, who, I don't know, who climbed Everest the first? And then you say Hillary. I think it was Hillary. No? I don't remember. And then you say, I don't know, how tall is the Empire State Building? And then you have like some number here. And at the end you say, what was there a question from before? I don't know. Who is the Queen of England? Yeah. Who is the Queen of England? And then you ask the model to predict the next word right here. Okay. And you do this in a closed book setting, which means you have no access to Wikipedia or whatever. Like usually these systems, they can go and query Wikipedia, but this system doesn't. So you just want to know what has the model learned about the world by simply absorbing giant amounts of text. So if somewhere in the training data, the fact that the Queen of England is Elizabeth II is present, it should complete this right here. And it performs surprisingly well, as you can see here. So it manages actually to outperform a fine-tuned state-of-the-art model that is fine-tuned on question answering, right? It has been built for question answering. And this model outperforms it by simply having a lot of language. So this here is the results on these open domain QA tasks. And you see right here, this few shot, it outperforms this open domain. And open domain means that the model can go and look at some Wikipedia page. And yeah, so this is pretty cool, but there are other things like the natural questions where it underperforms compared to this open domain thing. And they say this is mainly due to the natural questions being like, it's very much about factual Wikipedia knowledge and so on. Maybe like the question we just made maybe is more of a natural question type of thing. And the model is apparently not as good at that. But it's still impressive that the model is able to do this out of the box. Okay, so before I said something like, before we go into the experiments, I want the following. So I have like some sort of hypothesis, and it's not an uncommon hypothesis, that basically these things, these giant language models, right? They're just these transformers, layer after layer after layer, with their connections in here. What I think is happening is they are simply storing the training data, right? They are simply storing the training data in these connections right here. So usually you think of storing the training data in some form of, maybe we have like some module right here, some database module in the neural network, and it learns to query the module. But ultimately, if you train a neural network, what you have is data, and you train a function with parameters on that data. And ultimately what you're doing is you're distilling the data into these parameters. And you kind of hope to learn some regularities from it, but ultimately the information about your training data influences or determines your final parameters of your function. Now, I can imagine that if you have such a giant neural network with so many weights, like 170 billion weights, that you can pretty efficiently actually store the training data in that model. And when you ask this model now to do something, what it basically does is, what these people sort of argue is that it has learned these language tasks, it has learned to reason over language and so on. What I think is happening much more is it will simply go to the training data, since it has stored the entire training data in its weights, and it will sort of pull out the 5 to 10 to 50 training examples that are most relevant to what you put in, and it will sort of interpolate, right? It go to the training data, and it'll pull out a bunch of training samples that are relevant to the context you put in right now, and then it will sort of integrate those into the next word that's going to come out right here. And I think if you look at this paper in terms of this, so you always, right, you input a context, and the context is split into a task description, and then it is split into k different examples, and then it has a prompt. Sorry, this is the prompt. So the task description is please translate from English to French, and the k different things are k different translations. And then the prompt is, you know, what you should do. So it's like half of a K, half of one of these boxes right here. So these boxes have blah, 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 turns to blah, blah, blah. And then the prompt is simply without the right side. I think what it does is it will simply take all of this and it will go to its own training data, which it has stored in its weights. And it will filter the training data and basically take out the things that sort of pattern match, sort of regex match in a fuzzy way to this context. And then it will kind of interpolate these training examples in order to come up with the answer. I don't think there is reasoning happening here. And we're going to, if you go through the paper with this view, then you can, a lot of things actually make sense. And I think that we need what we need when people think of like explainable machine learning. They often think that if I'm going to input something, like I'm going to input an image into a classifier, and it comes out a certain class, car. Like the explainability should be, oh, which part of this image? Was it the wheels? Was it the hood? Which part of the image, which part of the input image is responsible for making that determination? What I think, especially in these language models, what we should do is, if the model predicts something right here, the next word, I think we should somehow have a method of determining which of the training examples that the model used to interpolate given this context, because I'm pretty sure these trainings you will find. So if you'll find that, for example, this weight and this weight and this weight was very responsible for making this prediction happen, I'm pretty sure you can somehow during training build an index of which 5 training examples had most influence on that particular weight or on this combination of weights. And then you can sort of go backwards and say, you made this decision right here, model. Please tell me which of the training data samples were responsible for making that decision. Actually pretty sure that already exists. Like, I'm never the first one to think of these things, though if I am, cite me. Cite the channel. No, but just an interesting way to think about this model, and an interesting way to think about kind of what would explainability even mean in a model like this. And my argument is, since it interpolates the training data, the interpretability should come from the fact of which training samples does it interpolate. Okay, let's go to translation. So in translation, as we said, they simply input the task and then the few examples and then the output. Okay, and you can see right here, what you can see is that, again, as the model goes up in parameters, the performance generally increases. And also you can see that the performance is pretty good every time that this model goes to English. So it goes, if the target language is English, which sort of makes sense because a large part of the corpus they train on is English. So being an English language model, it should be pretty good if it is asked to produce English, and it's not as good if it is asked to go into the different direction. Now, what you also see is that it is not really a difference whether you translate from which language you translate, but if you go to English, but it very much matters to which language you go if it is from English. So this sort of makes sense in that it is just trained on a lot of English data. And right here, sometimes they are on par with the state-of-the-art supervised methods, and also other times they outperform these methods right here. And these methods are unsupervised, but are specifically, so they don't have a supervised training data set that goes, let's say, from English to French, but they are built with this in mind, that they need to translate later. So they are sort of task specific, but don't have a supervised training set. And this model right here, it just learns whatever it learns, and it just does this language model learning. And at the end, just because it has seen some websites where language of both things appear, it can now translate reasonably well. Okay, now yeah, so the results here are a bit noisy, but it is still interesting to see that it sometimes even gets close to the supervised thing. Though they say that they are not familiar with the literature and are not sure that these numbers are, good. Okay. Okay, the next thing is these Winograd schemes, where you do have, where is the text? Here. Is a classic NLP task that involves determining which word a pronoun refers to when the pronoun is grammatically ambiguous but semantically unambiguous to a human. So these are sort of human-produced sentences where it's kind of a pronoun could refer to multiple things. I don't have a example present, but where do we have the right here? You can see that this model will outproduce a fine-tuned BERT large, but will not outproduce a fine-tuned Roberta large. So it is competing at least with the fine-tuned models that were made specifically for that task, right? Again, this is pretty interesting. And you also see that the larger models here, it starts to make a difference whether or not you give it 0 or 1 or more examples. Okay. So we'll get into the more interesting things right here. In this thing right here, sorry, where is it? Yes. This is the kind of a physical question, physical QA, where it is a bit of common sense reasoning. So you're asked to, these are like science questions. Multiple choice questions collected from a 3rd to 9th grade exams. And the physical QA asks common sense question about how the physical world works, and is intended as a probe of grounded understanding of the world. So it has questions, as I understand it, it has questions like, if I drop a ball, will it fall on the ground, or where will it fall, or something like this. And they say that they can outperform a fine-tuned state-of-the-art model on this if they go just high enough. And you can also see that there isn't much of a difference between 0, 1 and few shot the methods of this model right here, even though 0 shot is even higher than 1 shot. So this is probably just noise. But then you find out that they have an asterisk here. And this means that this is potentially a contaminated data set. So they have potential contamination issues. So what they found was there was a significant overlap between the this data set, and their training data set. And they only realized this too late because there was a bug in their deduplication code, and then they couldn't change it anymore. Because this model is so large that they couldn't restart the training because they've already spent like so much money and energy on it. This is crazy. I think these language models are getting so large that we should more think of it like we built the International Space Station or something like this, where it's a project where humanity sort of collaborates, or there's a big effort and you build it once, and whatever you have, right? So these good numbers here are because, or could be influenced by this contamination. And I think that's what's happening right here. Even though they will make the case that this contamination isn't really an issue, I can probably show you that it maybe actually is an issue. Because on the other data sets, the fine-tuned state-of-the-art model outperform the GPT-3 quite a bit. So, and also the fact that if you provide a demonstration or many demonstrations, it doesn't actually change that much. It kind of tells me that the model sort of already knows what the answer is and doesn't really need demonstrations, because it doesn't help. If you have the training data stored, or the test data, you don't really have to get demonstrations, right? So they have a few other things right here where on these COCA tasks they perform pretty poorly compared to others, or poorly, let's say. They perform well, but not particularly more well than a state-of-the-art. And they perform especially poorly on the reading comprehension. Sorry, that's the COCA. So in reading comprehension, what you have to do is abstractive, multiple choice, and span-based answer formats in both dialogue and single question settings. So basically you have to read a piece of text like this and then answer a question about the piece of text. Now this is something where I think you cannot really interpolate the training data super well, and therefore so you can't really just pattern match and interpret, because you have to do actual reasoning, and I think that's why the model performs poorly here. They do measure this on SuperGLUE, which is a NLP benchmark, and also here you can see it doesn't outperform a fine-tuned state-of-the-art model on these tasks, but it does outperform a fine-tuned BERT model slightly. So the BERT model is fine-tuned on these things, whereas GPT-3 isn't. But notice the tasks in which it does well and in which it doesn't do well compared to the state-of-the-art model. So for example, in the bool Q, it doesn't do particularly well, right? The state-of-the-art is 91, and it only has 76. That's quite a large difference. And I actually have the GLUE benchmark open here, and you can see this is the bool Q. So an example here would be, is France the same time zone as the UK? And then there is like a passage, and you need to reason about, from this passage, about whether or not this answer is true or false, okay? This is very much not language modeling. This is reasoning, and that's why the model is doing poorly here. Whereas in another thing, you see this, for example, this COPA right here. The model is doing almost as good as a fine-tuned state-of-the-art. And I have to stress, this model has never actually learned this task in a supervised way. It's simply a language model. And I have this COPA task right here. And these are the examples. So one example is the premise: the man broke his toe. What was the cause of this? And you have two different things that it could be. Either he got a hole in his sock, or he dropped a hammer on his foot. And the way you phrase it in this model is you would give the premise as the context, and then you simply ask the model, since it's a language model, which of these two things is more probable to come. And of course, it is going to select the thing that kind of happened more often in the training data. And, you know, broke his toe, the cause of breaking his toe, that is a hammer. This is entirely conceivable that a language model would know this, and with enough training data could sort of pull from the training data examples where hammer on foot and broke toe appear a bunch of times, and hole in sock would be rather unrelated. So as long as these questions are not too adversarial, constructed specifically that a language model can't solve them, the model is going to perform pretty well right here, right? So it's very interesting to see that if you view this as interpolating the training data, it suddenly makes sense where it's good and where it isn't good. So this was the super glue, and NLI, it is performing particularly poorly on NLI, which is the ability to understand the relationship between two sentences, right? So where the model classifies whether the second sentence logically follows from the first, contradicts the first, or is possibly true, neutral. Okay, so this is the reasoning part of this model is not given. It is simply recalling the training data and doing language modeling. Now they say, oh, we can test this. We can test this with synthetic and qualitative tasks. So they invent some own tasks. Since, you know, now it's pretty easy. Since you don't have to fine-tune the model, you don't have to generate an actual training set for a task. So you can focus on generating a test set, and you know, that's what they do. So they do something like arithmetic. So they say, okay, can we come up with a bunch of arithmetic tasks, for example, two-digit addition? So what the model would see so this is an example, and what the model would see is simply this as a context right here for the prompt. And if you give it examples, so if this is like one-shot learning, you would add the following numbers as a string, right? Then a new line. And then you would give it one example, like what is 11 plus 12? And with the answer, together with the answer is, I don't even know, 23. And then the prompt goes here. So what is 48 plus 76? And then you ask, what is the next word right here? What is the next string token that comes here? Now, the inference here is that if the model manages to do this, it can't simply, because these are all strings, the model basically has no clue how to do math. These aren't numbers to the model. These are just tokens as strings. And the inference is, if the model can do this, it must have learned, you know, some kind of reasoning ability. It must have learned to like perform some logic inside. So they go into two-digit addition, three-digit addition, four-digit addition, five-digit addition, and even multiplication and subtraction. And the results are right here. So as you can see, the lower parameter models, they perform pretty poorly. But as you go up the parameters, the big model is performing really well in the two-digit range, is performing also really well. So accuracy of, look at that, accuracy 80-90% in three-digit addition and subtraction. But then as soon as you get to the four-digit or the two-digit multiplication and so on, the performance drops. Now, they say that's because multiplication is harder and, you know, it's logically very computationally, you know, but the two-digit addition and so on, model has learned something about the world. I disagree. Because. So, here's the because. What you will do is you will simply, you simply recall the training data. So look at the two-digit addition. With zero shot, you already get 76%, but with one shot, you get 99%, and with few shot, you get 100%. So if you interpret this model as simply filtering the training data to pattern match, then it makes a lot of sense that the one shot would, like the examples here, would give you a much improvement. Because if you have a bunch of examples where please add, right, add, and then, oh, I erased our example again. So you have like 48 plus 72 equals blah, blah, blah. You have all of this. If you give more and more example, all of a sudden, this looks like a table. And they say, we made sure that the strings here, these particular strings, were not in our training data, right? So these strings never appeared. But I just have an issue with this deduplication stuff, because what can appear actually is what can appear is a table. And in table, often you have columns, and then another column will be the sum of these columns on the left. And if you are asked to pattern match, you'll naturally find websites, right? If you have a few of these examples, you'll find websites where the columns exactly refer to these things, and then you'll find the sum here. And if you filter for websites that appear to match your scheme in the examples, you'll find all the websites with a table on them where the column, one column is an addition of the others. And I can actually do that. So I went and I typed in just a bunch of these things. So 98 plus 45 is 143. 18 plus 55 is 73, I believe at least. And I can find, now Google makes it hard because they localize and everything, but you can still find, what you're going to find are tables and tables and tables and tables. And now I actually went to DuckDuckGo to basically say, they don't, really personalize it to me. And what's the first thing I find when I type in just these numbers is math, skip counting, missing sequence number, and a website where basically the answers are already given. Look at that. So all the model has to do is recall this particular training example from the samples it already has, right? And it will basically be able, in quotes, to perform addition. Like this is financial data. And another one where you have to subtract stuff, right? So I'm pretty sure all the model is doing here is interpolating the training data. And that's also why it performs worse if you up the digits, because longer digit numbers are simply less frequent in the training data. Multiplication is, first of all, less frequent, and second of all, it also results in larger numbers, which are less frequent, right? So it explains a lot. So I have my issues with people saying, this shows some reasoning. I don't think it does. The same thing here with word scramble. So in word scramble, they have different things. You see, okay, they look whether or not only 17 matches 0.8% of the math things are in their training data. It's like, no, you haven't searched well enough. And the rest of their deduplication, by the way, is also pretty weak, I would say, because they just look for like 13-gram overlaps between the training data and their test data. So they have these word scrambling tasks where they basically scramble words, and they ask the model to unscramble it. So, for example, this word is inevitably scrambled. So they always, they give like anagrams, and they give random insertion into the word, like this word right here, or they reverse the word. And they say, so this, I think this is the thing at the very beginning, but if you can see right here, also as the model goes up, then this improves. And they also say, well, this means maybe some kind of reasoning, but I think this is just, it's learning the language, and it's learning that the words the letters make up a word, and the letters correspond to word pieces or are associated with word pieces, and it always learns to English. A good task to check this would actually be to scramble words. So if you unscramble words, you always end up with an English word. So all it has to do is basically check which word has the highest overlap in word pieces. But you could do something like, please scramble this word, and then always count it correctly when any of the scrambling of the words. So instead of going from this to this, which you can simply solve by knowing the English language, but you would have basically no clue what the task is, that you don't have to understand that as a model. You could ask it to go from this to this, given a few examples, right? Then it would really need to understand what the task is, that it's supposed to actually scramble a word, and would need to learn that from its context given examples. But they, as far as I see, they don't do that. And again, I think it's recalling the training data. This is SAT analogies. So the SAT, or this test that US high schoolers take to get into college, and they say a typical example. Ooh, this is dying on me. No, it's scrolled. Okay. A typical example is the following. This I find pretty hilarious. Audacious is to boldness as sanctimonious is to hypocrisy, anonymous is to identity, remorseful is to misdeed, deleterious is to result, or impressionable is to temptation. Like, this is okay, I'm not a native speaker, but this is a hard question, right? And you have to see that these high schoolers, they're stressed. Like, this is very much a time-based test, so you need to make a decision quickly, while the model, of course, is basically able to sift through its entire training data in the time it takes the GPUs to perform inference. But it's still funny that GPT-3 achieves 65% in the few-shot setting, and 59% in the one-shot setting, 53% is zero-shot setting, whereas the average score among college applicants was 57%. So it outperforms the average college applicant. It's pretty funny, but you would expect the language model to have a pretty good grasp of these kind of synonyms and relations between words, because these are just absolutely statistical associations between words. So I found this to be pretty funny. And the last thing, and this is what everyone's freaking out over, is this news article generation, where basically they give it the beginning of a news article, and then they let humans decide whether or not the news article is written by a machine or by a human. And they say here, by contrast, mean human accuracy at detecting articles that were produced by the 175 billion parameter model was barely above chance at 52%. Human abilities to detect model-generated text appear to decrease as model size increases. There appears to be a trend towards chance accuracy with model size, and human detection of GPT-3 is close to chance. Okay. So what they do is they give, and they have some examples right here, they give the model the following input: the title, the subtitle of an article, and then this word article. And the model is supposed to complete the rest of the article right here. And you can also, do this in a few shot setting, such that the model basically knows that it's, if you give it a few examples, the model knows it is supposed to produce a news article, right? Okay. So there are two ways that you can think of this. First way, the model has learned the language so well, and it has learned to write coherent language and so on. It's learned to reason, keep context, and blah, blah, blah. Okay. Second way, the model sees this thing right here. It sees the few shot examples that it has before in the context. It will take them, filter the training data to, in this case, it just sees news articles. So to just news articles, it will take this thing, filter the training data even more to just the news articles that pertain largely to topics or words that appear in here. And then lastly, we'll interpolate the few training examples to produce this thing. Now, they argue that this isn't really possible because they have actually checked that this news article is not in the training data. But I have simply gone and taken I've really taken a random substring here. I've taken this substring, voted to strengthen the ban on the ordination of, just this substring. And I've put it into Google, and ba, I find a book with voted to strengthen prohibitions to ban LGBTQ people from being ordained as ministers. So it's, I find this. It's not the same article, but it's talking about the same incident the article talks about, and it is using the same language. Probably read the article, and the author is like, oh, I can't really, copy paste. That would be, not really cool. So I'll just kind of, write it in my own words, but largely the same thing. The Associated Press here, also a different article, see, different title than this one right here, but about the same thing. And also with the same language right here, voted Tuesday to strengthen the faith's divisive bans on same-sex marriage and ordination of LGBT clergy. And generally, so the argument this article wasn't in the training data is just not really something I buy in this case. So I think the article as such wasn't there, but many articles about this topics were, and I think this will just interpolate these. Now they say this was the hardest article for the humans to decide, and this here was the easiest. So it says, I don't know, Startuck's promise draws Megyn Kelly's sarcasm. It says, a year ago, Joaquin Phoenix made headlines when he appeared on the red carpet at the Golden Globes wearing a tuxedo with a paper bag over his head that read, I'm a shapeshifter, blah, blah. You would guess that Joaquin Phoenix would do something like this, but they say their human raters were US-based, right? And you see right here, it says, Megyn Kelly was not impressed, and she let him have it on The Tonight Show. Now, The Tonight Show is not where Megyn Kelly is, and US-based people would, I guess, know something like this and would immediately feel like this is wrong. So I think this thing is interpolated from a bunch of different news articles about this, and the interpolation just made it such that this person is on this show, which they aren't, and the humans noticed. Right. But it doesn't change the fact that it probably just went to the training data, filtered a bunch of articles about these words, and then interpolated, mashed them together. It is a good language model, right? It's very good at grammar. So it can interpolate different passages of text. And I feel that the really, really useful application of this will be sort of as a search engine, as a fuzzy search engine. So now I can input, for example, my machine learning research ideas, and what will output will be sort of an abstract of a paper that is kind of a mush together of other papers on the same thing, and that you can think of many applications. I don't think we have built something really intelligent here. And what this is though is pretty cool. They give examples like this here, where they make up a word and then ask the model to use the word in a sentence. So to screed is something, to screed something is to swing a sword at it. An example of a sentence that uses the word screed is, and of course what the model's going to do is it's going to take this, it's going to filter the training data for all of the instances where sort of this construction appears, like an example of using the words, which is mostly sort of dictionaries. Then it's going to not know that word, but it can interpolate it from all this data right here. And so the cool thing is it actually conjugates the word. We screed at each other for several minutes, and then we went outside and ate ice cream. So you can see how this comes to be, but I think it would really be fun to have a model that tells us which training data samples were used here. It can also correct English grammar, which is pretty obvious, though, again, it can never correct. So the input always here is poor English, good English, poor English, good English, poor, good, poor English, and then good English, and that's what the model is asked to output. And I'm actually not sure, pretty sure this here shouldn't be bold. I'm fairly sure this shouldn't be bold. This is given to the model. The model is only asked to produce this. Otherwise, I'd be actually impressed. But yes, nothing task specific is provided aside from the examples, from few examples as conditioning, and the poor English input, good English output framing. So the good English output thing here should not be in boldface. Authors, if you're listening, this should not be bold. Thank you. Okay, but again, it is always, as you can see, it's too good English. It's always the target is good English. Whereas if the model really understood the task, it should also be able to do the inverse. It should be able to produce something poor from something good, because then you eliminate the fact that it's just a good English language model, right? Because it can basically produce something like this without having a clue what the task is. It will simply, you condition on this input, and it will simply output this sentence because it's very likely, because it's already almost here, and it will output it in better English because it's a good language model, right? It's a good English language model. So, yeah. So they measure this overfitting, the degree to which their their test data is in this common crawl thing, and they say they have a conservative bound on how many % of the data in the data set are clean. And as you can see here, they measure then how much the performance differs to up or down if you only evaluate on the clean portion of this data set. But again, their deduplication is so weak. They do like n-gram deduplication, whereas I think you should really, like in the news articles, you should really do sort of much more fuzzy deduplication, much more of a meaning deduplication. If you then want to argue that the model has learned to reason, like if you simply want to argue that the model is a good language model, fine, right? But yeah. And also look at this, like I would expect of a data set, a test data set, if you have like a natural questions data set that is constructed from Wikipedia pages and you have the Wikipedia page in there, you can either the entire thing is clean or none of it is clean. And also these Winograd data set, if this data set somehow leaked into the common crawl corpus, either the entire thing is clean or none of it is clean. I just have kind of problems with the fact that there are so many in-between things right here. And yeah, so I'm not convinced here that this deduplication, I still think it's a cool thing, but I think it's mostly a training data filter and interpolator rather than actual reasoning. And they go through some of the limitations here, and the broader impact. This broader impact statement is like 5 pages long, and yeah, okay, bad people can take the model to do bad things, okay. And that's pretty much it. So what I appreciate here is at the bottom, they have basically all the results, but also a lot of task descriptions, like how they framed each task, more outputs, and they give more outputs on their website, right? So you can see here how each of the tasks was framed, where you always have, this here is what the model sees, and then this is what it's asked to produce, right? So you have this for many of these things. And so on Squad, you have this context and the question. Okay, so the context is actually in there. I didn't know that before. But you have the context and the question, and the model is asked to complete something right here. So you can look at how the model sees tasks, and maybe you can evaluate for yourself how difficult you think these tasks are. All right, I hope this was informative. It is a long paper, therefore it is a long video. If you're still here and haven't subscribed yet, do, maybe, if you like this. If you want more, leave it a like. Tell me in the comments what you think of it, whether you think it's actually AGI or not, and I'll see you next time. Bye bye.